Now we're going to talk about units. Units are very, very important. Okay? Here's an example. Back in 1999, NASA had this Mars Climate Orbiter that they sent out, $125 million. It was supposed to be in a stable orbit around Mars and help us study Mars. It gets out there, and somebody made a mistake with the calculation. They later, after investigation, they concluded the root cause of the loss of the spacecraft was a failed translation of English units into metric units. They were calculating what the orbit needed to be, and one group of scientists was using centimeters, and one group was using inches, and apparently they weren't putting units on their measurements, and so the orbit was too low, and it got sucked in and burned up in the Martian atmosphere. Yeah, oh, sorry. I forgot to put a unit on that. The good news is your mistakes with units will not be so costly, right? But we should always, always, always be writing units on things. Units are important in everyday life. You go to McDonald's and you'll say, I want 2.
Yeah, someone came up to the counter.
2 hamburgers? You want 2 coffees? You want a number 2 meal? Right? We need more information. So the number part of the measurement is, of course, important, but the unit is equally important. So you can increase your scores on things by taking care with your units. There are 2 common unit systems used in the world, the metric system and the English system. There's another system called the International System of Units, or the SI system, and that is based on the metric system, and for our purposes, it's the same. The differences between the SI system and the metric system I don't think are worth talking about, so I won't. So these are examples of metric units. Length is measured in meters, mass in kilograms, time in seconds. That one's familiar, right? Temperature is measured in kelvins. Amount of stuff, of substance, is measured in moles. We'll talk about that later. And these last 2 are there just to complete the table, but we're not going to use them. It's helpful to have a general idea of how big these metric units are so that you can recognize when you make a big mistake, okay? So if you calculate that a basketball player is 7 meters tall.
That's a 30-foot man.
Yeah, so a meter is about 3 feet. So that guy would be 35 feet tall. That's ridiculous, right? But if you don't know how big a meter is, you won't see that, right? So a meter is very close to a yard. So this is actually a meter stick, which is different than a yardstick. It's 1 meter long. The yard is up to here, really close. So ballpark, the same. Meter is like a yard. For mass, we're familiar in everyday life with using pounds or ounces. In the metric system, we use grams or kilograms. So a kilogram is about 2 pounds. That's close enough for seeing if you're way off base. So that's the measure of mass. Mass and weight are actually slightly different things. Weight measures the force of gravity on an object, whereas mass measures the amount of matter. So if you stay on Earth, which I think we're all planning to do this semester, anybody planning to go on the space station? I didn't think so. As long as we're staying on Earth, we can use mass and weight interchangeably. But interestingly, even as you go around the Earth, gravity changes slightly. But we're not going to worry about anything that picky. So how big is a gram? Well, a nickel is 5 cents, and a nickel weighs about 5 grams. So a gram's really small. A kilogram is about 2 pounds, and a gram is 1/5 of a nickel. It's really small. So it's helpful to just have an idea. Time, a second is a second. You can get a lot more complicated, though, and they keep changing the definition of what a second is. You can read that. I'm not
How
going
do
to.
you change the definition of a second?
Well, all of these things are defined, and they have to be initially defined somehow. And people have to agree on it.
Okay, 60 seconds to a minute, boom, that's it.
Yeah, but how long is the second?
Well, how long is the minute?
Well, the minute is 60 seconds, but they have to decide on how long is the second.
Keep it the same. It's not like it's going to change.
So
It's a
temperature
concept.
is a measure. Kelvin is a temperature. Let me start that over. The Kelvin, a measure of temperature. We just talked about kinetic energy and thermal energy. So the temperature of an object is a measure of its average kinetic energy. So my soda here is cold. It has a lower temperature. The molecules have lower kinetic energy. If I had a hot cup of coffee, I don't like coffee, but if I had a hot cup of coffee, it's a higher temperature, those molecules have more kinetic energy. And we measure that using units like Kelvin or degrees Celsius or degree Fahrenheit. So temperature is the average kinetic energy, and differences in temperature determine the direction of thermal transfer. So thermal energy, what we commonly call heat, and this we know from just personal life experience, does heat go from the hot thing to the cold thing, or from the cold thing to the hot thing?
The hot thing, cold.
It goes from the hot thing to the cold thing, right? Because that's causing a lowering of the potential energy. Okay, so we are going to encounter 3 different temperature scales in our class this semester. The Fahrenheit scale is what the weatherman uses, what your doctor probably uses when they ask you, well, what was your fever? What was your temperature? They're talking Fahrenheit. So degrees Fahrenheit. For Fahrenheit, water freezes at 32 degrees and boils at 212 degrees. Those are kind of typical of English units. The numbers seem to be a little random. Like there's 3 feet in a yard, but 12 inches in a foot. Where do they get these numbers? The thing about the metric system is everything is based on powers of 10. So we don't have any weird numbers like that. 64 ounces in a gallon, anything like that. So here we have boiling at 212, freezing at 32. The Celsius scale, which is a metric scale, is based on water freezing at 0 and boiling at 100. Because you have to assign a temperature. So water freezing and water boiling are very easy to obtain. It's like, well, I can make this, I've got ice water. Ice in water is always going to be the same temperature. It's going to be 0 degrees Celsius. So I can use that to calibrate things. If my water is boiling, it's going to be 100 degrees Celsius. I can use that to define things. So Celsius is what scientists use. Both of these scales, though, allow for the possibility of negative temperatures. You can have a temperature that's below 0. So the Kelvin scale is also called the absolute scale. And this scale has no negative numbers in it. And it avoids that by placing 0 at absolute 0. And so absolute 0 is the temperature at which molecular motion theoretically stops. So particles are not vibrating at all, just completely frozen. You can't get lower in temperature than 0 kinetic energy, right?
They
So
start
of course,
shaking backwards.
Hmm?
They start shaking backwards.
It doesn't work that way.
They do this.
So of course, scientists are out there saying who can get the closest to 0, right? Because that's a challenge. Yes.
Are they able to do it right now to get to absolute zero, like scientifically?
I haven't kept up on that research. I think the last I heard was 0.4. So really close.
It's pretty much impossible because energy likes to reach equilibrium. It likes to branch out and kind of get everything to that same point.
Mm-hmm.
So as much as they can try to get it closer and closer, energy is going to continue to flow in.
Yeah.
And you can't stop that.
Yeah, it's not a simple matter.
It's not like you could just build a wall and it goes into that.
So on the Kelvin scale, water's going to freeze at 273 and it's going to boil at 373. And you're like, well, those are crazy numbers. Where do those come from? Well, in the Celsius scale, if you extrapolate down to the lowest possible temperature, it's negative 273. So the Kelvin scale, the kelvins in degrees Celsius are the same size unit. The difference is that 0 is in a different place. Celsius and Fahrenheit scales differ in the size of the degrees and they're 0, so their relationships are a little bit complicated. And so to convert between Celsius and Kelvin, we need to use an equation. Here, you plug in the Fahrenheit temperature and subtract 32, take that quantity, divide by 1.8. That gives you the Celsius temperature.
I took this class last time. I have that one memorized. So when I'm talking to friends in
Oh, good.
other parts of the world, I use it.
Because in many other countries, they report weather in degrees Celsius instead of degrees Fahrenheit. And so they'll say, it's 25 degrees. Ooh, that's really cold. No, actually, that's 73, right? So sometimes it's useful to be able to do that conversion. Between Kelvin and Celsius, the relationship is just a difference in 273.15. So take the Celsius temperature, add 273.15, and that's Kelvin. I will give you these equations when I give you an exam. What's important is that you're able to use them, not that you can memorize them. So let's do an example. Gallium is a solid metal at room temperature, but will melt to a liquid in your hand. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on A, the Celsius scale, and B, the Kelvin scale? So this is a word problem, right? We're not just giving you a math equation. We've got sentences with words. When I was a kid, they called them story problems. Doesn't that sound friendlier? Oh, it's a story. Yeah. Our stories here are very interesting. Some people have a real hard time changing the story, the words, into a mathematical equation. Okay? My experience is people either naturally can do it or it's a struggle. It doesn't mean you can't do it, though. You can become better at it. Remember growth mindset? You're not good at it yet. And so one of my goals is to teach you to become better at solving word problems, because there's a whole bunch of word problems in chemistry and in real life, actually. So the first step is always read the whole question. Okay, so I read the whole question. And then look for numbers. So here I have a number, because we're probably going to use those numbers. And then let's look at what are they asking us to find. So question words, what is? So here we want the temperature in Celsius and the temperature in Kelvin. We can't successfully do a problem if we don't know where we're going, right? So the number is what we're going to start with, Basically, this comes down to convert this temperature in Fahrenheit to Celsius, and then convert it to Kelvin. Temperature conversions, we use an equation. So the first one, we're taking 85.6 degrees Fahrenheit, and we're going to convert that to degrees Celsius. So we need the equation. So you can go look it up if you don't have it memorized. The temperature in Celsius is equal to degrees Fahrenheit minus 32, the quantity divided by 1.8.
29.4.
So we stick our temperature in here, and then we get out our calculators. You need to be a little bit careful here, because you want to make sure that you complete the subtraction before you divide by 1.8. So you might want to use parentheses, 85.6 minus 32. And I press the equal sign, and that finishes that, and then I divide by 1.8. And so my calculator is showing me 29 point.
4. A bunch of 4s.
Well, I'm getting 7s.
Oh, I forgot the 0.6.
Yeah. And then the unit on that would be degrees Celsius. Now, we skipped ahead a little bit and talked about significant figures. Is that a reasonable number of significant figures? So if we look at this equation, we've got subtraction and division mixed together, which means that using the sig-fig rules on that is going to be a pain in the butt, right? It's just going to be a pain. We don't actually need to do that for temperature conversions, because a Celsius degree and a Fahrenheit degree are very close to the same size. 1.8 factor difference, that's less than times 2, right? So they're very close to the same size. So if this temperature was measured to the nearest 1/10 of a degree, then when we convert it, we can say we're going to report this to the nearest 1/10 of a degree. So because this one had 1 decimal place, I'm going to round this one to 1 decimal place, and I'm going to say it's 29.8 degrees Celsius. So round temperature results, from converting to the same decimal place.
You don't care if we put like this habit, because when I do an approximate, I always do like little tildes.
You can write that in there, yeah, but all measurements are approximate, so then you have to write it on everything.
Well, it's just habit from that value.
That's fine. Okay, so now we need to convert to Kelvin. The 2 equations we had, one was Celsius and Fahrenheit, and the other was Celsius and Kelvin. I didn't give you one for Fahrenheit to Kelvin. I mean, you could come up with one. One exists. It's just not even worth thinking about. It's just faster if you have to go Fahrenheit to Kelvin, take Fahrenheit to Celsius and then convert it to Kelvin. So I'm going to take this value that I found in Celsius, so not degrees. Kelvins are just Kelvins, not degrees Kelvin. It's the Celsius temperature plus 273.15 if we're wanting to be precise. So I'm going to take the Celsius temperature that I already calculated and take 2 extra digits with you to avoid rounding errors. So 29.7, those are my sig figs, and I'm going to write 2 more digits. When you write those 2 extra digits, if you want to round this correctly, you can, but if you don't want to, you can just not. It's not going to make a difference in your final answer. That's part of why I chose 2 digits, and you don't have to think as much. So we're going to take that, and we're going to add 273.15. And so I get 30, 302.927. Now, and that would be kelvins, where should we round that?
Second.
At the whole, nearest whole number, I would think.
The second decimal would be here. I think the first decimal. Okay? So I'm looking at my original number. And this has one decimal place. It has the first decimal place. So then in my answer, I want to keep just the first decimal place. So I'm going to keep the 9.
If we were to convert from, you said what, Kelvin to Celsius?
Mm-hmm.
Fahrenheit to Kelvin, would we use not the 85.6 Fahrenheit? Sig figs?
Regardless of the direction or units that you convert through, you can always use this rule.
Okay.
Same decimal place. I like it because it's just easy. And actually, it's better than sig fig rules. So that's kind of nice too. So one of the things that's on the worksheet today is practicing some temperature conversions. Any questions?
Ooh, we're getting behind here. Oh, that's a lot.
Okay. What makes the metric system so beautiful is that it's all based on powers of 10, and we don't have these weird random numbers to remember, like 5,280 feet in a mile, right? Everything's a factor of 10. And so we express those factors as prefix multipliers. And they change the size of the unit by powers of 10. Well, why do we need to change the size of the unit? We want to be able to use a unit that's similar in size to what we're measuring, right? So we're more comfortable with the English system. So if we think about, well, the distance from my house to Fresno City College is about 30 miles. Why do we use miles instead of inches? Yeah, a couple of Snickers, because that's ridiculous, right? Because you'd have this ginormous number, right? So we tend to use units that are similar in size to what we're measuring. So the metric system has this whole collection of prefix multipliers so that we can tailor make the units to be a good size for whatever we're doing. So the first example here is a kilometer or kilometer. So this prefix kilo means 1,000 or 10 to the 3. So if you have 1 kilometer, it's 1,000 meters or 10 to the 3 meters. Because this kilo and 1,000 or 10 to the 3, those mean the same thing. So they decided lowercase k, kilo, is going to be an abbreviation for multiplying this by 1,000. So when you're reporting the measurement, you choose the prefix multiplier that's similar. And there's 2 questions on the worksheet about that as well. Okay, look at all those guys.
I'm going to assume, go a little bit here, that you meant, there's the typo here.
On the previous slide?
No, on a forward.
On this one?
No.
On the previous slide?
No, first, going up one.
Next one?
Yes,
I'm not there yet.
I know.
We'll look at it when I get there. Okay, so these are metric prefixes. They all have a 1-letter abbreviation. Capitalization matters here. This is the multiplier expressed in decimal notation. So many zeros. So don't look at those. Don't look at those. The ones you want are over here. 10 to the something. And if you look at these exponents, they're changing by 3. 18, 15, 12, 9, 6, 3. Now, right in the middle, there's a couple of weird ones, but then we've got minus 3, minus 6, minus 9, minus 12, minus 15, minus 18. So essentially by thousands, right? So you don't need to memorize all of these, but you should memorize some of them. Kilo, centi, milli, micro. Those are the ones that come up a lot in Chem 1A. There were a couple other ones that I put on the list of things you should memorize. So if you see micro, you should be able to tell me that's 10 to the minus 3. And its symbol is this funny thing here. Micro. Oh, -6. Thank you. I was just testing you. Yeah, 10 to the 6. It's right over here. So those are the ones that are most important to remember. That mu is the Greek letter M because we already used the capital M and the lowercase m, and micro starts with an M, and we ran out of M's, so we went to the Greek letters.
There's the typo. Capital M, lowercase m. Which one is it? I'm going to assume lowercase.
On this unit,
Yeah.
it's megameters.
Oh.
So the capital M is the prefix, mega. So the question here, how long is 4.5 megameters in meters? Well, we need to know what mega stands for. Mega stands for 10 to the 6. Okay? So what we can do is we can write this. We can write the 4.5. Instead of writing capital M, mega, I'm going to write what it means. Times 10 to the 6 meters. So this is just a lot shorter, easier to pronounce, all of those good things, than this, right? But the capital M is just an abbreviation for times 10 to the 6. That's all the metric system is doing. Okay? Metric system can be kind of intimidating to people. I want you to go for it, okay? It might take a little bit of struggling, but once you see how it works, you'll say, oh, I can remember that. You just have to understand it first. And that might take a little struggling, right? Growth mindset. You can get better at it. Here we have 7.13 times 10 to the minus 9 liters is equivalent to how many nanoliters? Well, I need to know what nano means. Nano sounds like 9. Nano, 9-0. That's how I remember this one. It's 10 to the minus 9. That's what nano stands for. So if we want to express this in nanoliters, oh, look, there's a times 10 to the minus 9 sitting there. So instead of this, I'm going to write nano. And this is 7.13 nanoliters. This number here doesn't change. It's just the zeros in front or behind it that are going to change. We're just really moving the decimal point around. Any questions? Recognize that person?
Mm-hmm. I don't remember this.
Yeah, so that's me sitting in a cubic meter. Went to a museum and they had one, and I'm like, here, take my picture, I could use this. So we've talked about units for length and mass and stuff like that. There are also another group of units called derived units, and they are combinations of those other units. So a rate of speed in miles per hour is a derived unit involving miles and hours. In the metric system, we would use meters per second because those are metric units. We know what volume is. It's a measure of space, right? So if you think about something like this cubic meter, how do we calculate the volume of that? Well, we take one side,
Meter squared
right,
or cube.
and we take another side, and that guy there, 1 meter. And we say, well, the volume of that is the length times the width times the height.
Meter cubed. So just still be 1.
It would still be 1. But 1 meter times 1 meter times 1 meter
It's still 1 meter.
is 1, but now the unit is meters cubed. So any length unit, if it's cubed, is a volume unit. So we'll typically use things like cubic meters or cubic centimeters to measure the volumes of solids. For liquids, we'll typically use liters or milliliters. It's kind of the difference between like a fluid ounce or a gallon versus cubic inches. I don't like that slide. So here is a table of common units and their equivalents. We have the green and yellow cardstock handouts over there, which students love because there's so much information on them. There's unit conversions on there as well, but in my opinion, there's way too many. We should be able to do pretty much all the problems just using these. So I would encourage you, go on Canvas, take a screenshot of this, save it in your device so that you can just pull it up anytime you need a conversion factor. Google will also convert units for you, but Google is not taking the class, right? So you could use Google to check your answer, but you need to be able to write out the conversion like I'm going to show you so that I can tell that you understand how this is working, okay? So when we look at this is going to be between the metric system and the English system because we don't need a table to show us between kilometer and meter because we know what kilo means, so we can make that conversion factor, just understanding the metric prefixes. So most of these are going between metric and English system. In terms of significant figures, if you're switching systems, it's not an exact relationship. So when they say 1 kilometer here, they mean exactly 1 kilometer is 0.6214 miles. That has uncertainty here. It has 4 significant figures. The one exception in here is this guy. An inch equals 2.54 centimeters. That is exact. It was really close to that, and they actually redefined the inch, so it was exactly 2.54 centimeters, just to make everybody's life easier, I guess. The one very useful conversion that's not on here that students often forget, a cubic centimeter is the same as a milliliter. And I guess that's why, that was the point of this slide back here. So let's talk about it for just a minute. So here's a cube. It's 10 centimeters on a side, and each of these is a little cube of its own. So we have a 1 cubic centimeter here. It's 1 centimeter on each side, and if we take these all and stack them together, it's going to take 1,000 of those to make this cube that's 10 centimeters on a side. So 10 centimeters on a side, so that's going to be cubed. That's equal to 1,000 cubic centimeters. And that's the unit we call a liter. So this little guy then is 1/1000th of a liter. 10 to the minus 3. So 1 cubic centimeter is equal to 1 milliliter. Another derived unit is density. Density is the mass divided by its volume, mass of an object. So for liquids, we typically use grams per milliliter. For solids, grams per cubic centimeter. There's a question about this on the worksheet. Density is a physical property that depends on temperature. So density comes from the relationship between mass and volume. Does mass change with temperature?
No.
No. Mass is constant. Doesn't change with gravity either. Mass is just mass. Does volume change with temperature?
Yes and no, kind of.
Yeah. So if you take a balloon and you heat it up, it gets bigger. And you cool it down and it gets smaller. You take your water bottle and you stick it in the freezer and you forget it, and you come back and it's popped because the water expanded as it froze. Volume changes with temperature. So when we're looking at densities, they're always going to specify the temperature. And we just want you to know why they do that. Another kind of property, intensive versus extensive. So intensive is kind of like something that is intrinsic to the substance. It's a fundamental part of it. It doesn't depend on how much of the stuff you have, right? So the density of something doesn't depend on how big the object is. If the object is bigger, its mass is bigger, and its volume is bigger, its density is the same. Melting point. You take a small piece of ice or a big chunk of ice. They melt at the same temperature. It doesn't depend on how much. The color. Take a piece of chalk. Don't tell me on your instructions. So here's a piece of orange chalk. I broke it. I usually do this writing with it, so. Did the color change? Nope. That's an intensive property. Things that do depend on how much stuff there is are called extensive properties. So intensive properties can be used to help identify a substance, because it doesn't matter how much stuff you have, that thing is going to be the same. But extensive properties like mass, length, and volume do change. So my poor little piece of orange chalk here, the length changed when I broke it, right? The mass changed as well. I can't use the mass of this object to decide what it is. The color of it, its appearance, is going to help me. I could measure its density. That would give me another important clue that might help me identify it. So let's do this example of calculating density. So a man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water, and the question is the ring made of platinum? So we read the question, and we're going to look. There's some numbers here. Let's highlight those. And then what are we trying to find out? Is the ring made of platinum? Well, that sounds like a yes or no question, doesn't it? How do I take 3.15 and 0.233 and get yes or no? What can we use to identify a metal? The density. Well, yeah, but that's not going to, the periodic table isn't going to help us with this one. We could use the density. So let's give ourselves a first step of find the density. So we're going to take this 3.15 grams and 0.233 cubic centimeters. That's what we're given. And we're going to find the density. And then if it's platinum, the density should match up with the density of platinum, right? And if it isn't platinum, it won't match up. So then we'll look up the density to see if it's platinum. One thing that might be a little new is this idea of this: the ring displaces this much of water. It's not coming out and saying the volume of the ring is 0.233 cubic centimeters. We should be able to recognize that cubic centimeter is a unit of volume. But how would this happen? So, if you had a graduated cylinder and you put some water in it, and then you drop the ring into it, then the water level is going to go up, right? If the bathtub is full to the top and you get in, what's going to happen? A whole bunch of water is going to come out. That was what, somebody did that apparently. That's how the story goes. And that was a big revelation. So the amount of water that is displaced is equal to the volume of the object. So you can look on your graduated cylinder and see how much the volume of water changed, how much it went up, and that is the volume. So this is the volume of the ring, and that's the mass of the ring. So density is the mass divided by the volume. So our mass is 3.15 grams, and our volume is 0.233 cubic centimeters. So 3.15 divided by 0.233 equals, and my calculator is giving me a mess, so 3.5. What I can do is I can look at the numbers that I was starting with. They're going to determine the number of sig figs in my final answer. How many sig figs should my final answer have? 3. So I've got 3.15. That's 3 sig figs, and this is 3 sig figs. If you said 2, you were probably thinking of the rules of adding, right? The decimal places. So multiplying and dividing is the number of sig figs. So I'm going to end up with 3 sig figs. So those are the 3 significant figures, and because Mrs. K said so, we're going to write down the next 2 digits. And then the units, those aren't going to cancel out or anything. They're just going to stay there, grams per cubic centimeter. Now when I report my answer, I go back and I round that to the correct number of significant figures, and there's the density. How do we find the density of platinum? We look it up.
I already got it here. 21.45 grams per cubic centimeter.
Okay, so 21.4.
Yeah.
So does that match up?
No, it does not.
No. So platinum is 22 point, was it 22.4? 21.4.
Look at my handwriting.
So, yeah, he was right when he thought it felt a little light, right?
Either gold or silver.
It could be gold or silver, or it might be even like, steel or something. It's obviously going to be a combination of things. That density matches up best with mercury, but obviously it's not made out of mercury because mercury's a liquid. So here's a conceptual question about density. So the density of copper decreases as the temperature increases. This happens with most things. What change occurs in a sample of copper when it's warmed from room temperature to 95 degrees Celsius? So we don't need to calculate, but might be helpful to make notes to ourselves. So density goes down when temperature goes up.
So it expands.
Yeah, so here we have the temperature going up. That means the density is going to decrease.
It gets bigger. Question is it going to be a noticeable amount larger?
So the density decreasing isn't on any of those answers, is it? We've got the sample becoming lighter, the sample becoming heavier. That's talking about the mass, right? Does mass change with temperature? No. So those are wrong. The sample expands. That means the volume's getting bigger. Or the sample contracts, meaning it's getting smaller. So the density is equal to the mass over the volume. If my volume gets bigger, what happens to the density? It gets smaller, because I'm dividing my mass, which is the same, by a bigger number, right? So if the volume expands, then the density is going to